Okay, so welcome to this lecture series on model-based reinforcement learning. What we will cover in this lecture series is we want to introduce first why model-based reinforcement learning is something that we want to aim for. We will describe what is a model, what are possible inputs to that model, and what is a good model. And then most of the lecture will actually be concerned with the topic about how can we actually use a model in reinforcement learning. Turns out there is actually two different ways of doing it. The first one is background planning, which will be introduced first, where the basic idea is actually to introduce models during the training of reinforcement learning agents in a background process, while online planning, we really do use models actually during the deployment of such agents to actually plan through a task in the environment. We will then end with some ideas to auxiliary tasks, and we will end up with topics that arise in the real-world application of model-based reinforcement learning, which is actually mostly be dealing with how to do with uncertainty in our models. Okay, so let's get started. So first on a motivation why actually to use model-based RL. So also one thing to mention at this point is many parts of this lecture videos are actually adapted from this model-based RL tutorial from last year's ICML conference. I will be mixing a little bit of this tutorial with the course of Sergey Levin and actually come up with this model-based RL course. And it turns out that in the MBRL tutorial there was a nice quotation or citation of Kenneth Craig, who was a cognitive scientist, and he says, if the organism carries a small-scale model of external reality and of its own possible actions within its head, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize the knowledge of past events in dealing with the present and future, and in every way to react in a much fuller, safer, and more competent manner to the emergency which face it. So the idea of having access to a model that describes the world and its dynamics, and then to use this model to actually make better decisions turns out to be incredibly powerful and underpins a lot of the advantages that we have seen in numerous applications in the real world. So this actually, this sentence is actually very well describing actually the idea behind model-based RL. Model-based RL has, we have seen successful applications of model-based RL throughout many actually application areas that we are using RL in. I'm just mentioning here six applications. So the first one is robotic control, which is like the major area which we actually introduced, where we actually use model-based RL. It's just one particular example. So in this application, a robot needs to grasp brakes from a Jenga tower, and actually we can use models that describe actually how all those pieces fit together and how all the blocks interact with each other, and also knowledge about if you pull one of them out, actually how this influences actually the rest of the block, and then we can actually leverage a model that actually describes this physical dynamics of the blocks, and this enables actually the robot to more accurately predict what's going to happen and hence to choose its actions appropriately. Another example also that's often be dealing with robotics has to do with the safety of robotics, especially when they are actually to pose a harm to humans, when we actually are in some human-machine collaboration environment. Actually, what you do not want to do is you do not want to. So actually, you want to have a planning model that actually describes how your robot behaves, and you do not want actually that the robot is actually harming people or even themselves through crashing into walls or indoors or something like this. And actually, we can avoid that from happening if we give the robot a model of the world, and that actually allows it to deduce how certain it is about what's happening in the world, and we can actually exploit the measure of uncertainty to predict when an action that is going to be executed should be considered unsafe or not. And if we are dealing with an unsafe operation, then we can maybe back off to some safe behavior, or actually change the action a little bit to be safe. We also see this a little bit in the dependable RL lecture. Another application which also involves safety is in the context of human-robotic interaction, in this case an autonomous driving example. So in this example, it is very helpful if the car would have an explicit model about the world and how drivers and other cars are going to behave. So whether they're going to accelerate or slow down within the local intersection here, for example. So actually, if you know if the car is braking, then you can accelerate, and if you know that the car is accelerating, then it's better for you to actually brake. This could actually prevent accidents from happening, or actually minimizing the risk of accidents to be happening, which is also something we will also discuss in the use case in the dependable RL lecture. So a very famous example where we actually see model-based RL is in games. So what you see here is AlphaGo, and which is actually this is a very popular example of using models together with reinforcement learning to actually exploit knowledge of the game in this case. So AlphaGo actually relies on, at its core, relies on having a model on how actually the rules of the game actually how they actually operate, and so actually where you actually can place stones, and what are the winning conditions of a game and things like this. And actually, if you have this information embedded into your model, then you can actually use this model to search over different possibilities of actions, and you can evaluate them because you actually know what kind of sequence of action will have which probability, and then you can actually select the best one of them. In science, then it's actually the same idea that you have in AlphaGo, where you can actually look for the synthesis of complex molecules. Actually, so the idea is that you want to actually synthesize a given molecule because it actually has some certain properties, and there's different kinds of actually how you can actually build such a molecule. And if you can actually model how on the atomic level how little molecule parts interact with each other, then you can also simulate how they can be combined. And having a model of all these interactions and all these behaviors on the atomic level lets you actually do model-based reinforcement learning to actually find synthesis plans for complex molecules. And also another area of research that it's very popular in is the area of operations research in here. For instance, operations research and energy applications, which is also something that we also mentioned in the introductory lecture. And here's the question, so in this paper the question is, how can we actually make good use of renewable energies? So you have a decentralized storage system, you have a demand on the other side, and you have renewable energy sources like wind or solar and things like this. And the question is, how can you allocate energy with that actually meets the demands and that actually stores energy in the battery and things like this. So you can describe very much of this using models, and if you have the models and you know how actually different things how they operate with each other, then you can also leverage these models to make better decisions, and in the end to ideally use more renewable energies in the end. Okay, so this for some application motivation. So the question is now, why should we actually use model-based RL? So so far, so in the introduction, in the beginning, we actually introduced all the dynamic programming ideas, and actually where we actually tried to solve MDPs. And what we actually did is we did model-based RL because we had a model on the environment and we solved that MDP using this model. And then we said, okay, model free is much better because we have all the information and we don't use it now. Actually now the question arises, why do we want to go back to the original situation? And it turns out that there's a lot of dimensions that we can actually compare model-free to model-based RL methods. And while we actually had in the beginning the issue that we did not have access to a model, lets us introduce all these nice and state-of-the-art algorithms such as policy gradients and DQNs, which actually solve incredibly successful along different tasks. However, there's also model-based RL that we can still use on the other side. And it turns out that at certain areas, model-based algorithms actually outperform model-free algorithms. And okay, let's maybe talk this through a little bit. So the question is actually about the asymptotic rewards. So if I talk about asymptotic rewards, I mean that that the performance of our RL agent is actually asymptotic in the returns it gets in the performance over the course of training. And I mean, in the end, model-free reinforcement learning actually outperforms everything that's there if you train them for long enough, with enough data, actually. And usually this is something that you can run in simulation, that you can do this. However, it's costly. On the other side, model-based RL has lower asymptotic performance in terms of returns and rewards. However, this really depends on the specific model-based RL method that you're actually using. And even lately, there is model-based RL algorithms that actually outperform model-free versions. The next dimension to actually compare with is computation at deployment. So actually, model-free RL, if you deploy an agent with model-free RL, you just put in the state or the observation into a neural network, and you just perform a forward pass, and what you get is the action that you're gonna take. So it requires a single forward pass through a network, which is quite inexpensive. So this is like you can do this easily. However, it depends for model-based agents a little bit, depending if you're doing background planning or online planning. However, usually what you want to do in model-based RL, you want to during the deployment of the agent, you want to plan certain action sequences and how they actually perform in the real world, which usually means that you have a little more effort when you deploy a model-based. So you have more computation effort at deployment if you haven't deployed a reinforcement learning agent. So on the other side, actually, when it comes to data efficiency, what you see is that model-based RL agents are really much more data efficient than model-free RL agents, because you actually have more information that you gather inside your model. It doesn't matter if you actually learn the model or if you have a model given. It turns out that in terms of sample efficiency, model-based RL algorithms usually outperform model-free algorithms by areas of magnitude. You see that in the summary. Then the thing is, what is about if you have a changing reward system? So what actually happens if the reward system in your environment changes? Something like you have a new task description or something changes. If you have a model-free agent, this is really quite a complicated issue. You have to adapt a given policy or value function actually because if you change the reward system, all your value function would change for value-based RL. And your policy might also be different. And actually to adapt a given policy or value function to a changed reward system is something that is really highly non-trivial. However, if you have a model-based RL agent, the model, so the dynamics is still the same, you really need to adapt the rewards, which is in many model-based RL agents really something that you get by free because you do planning in real time. So on the other side, if the dynamics are changing for model-free RL agents, this is really the same if the rewards would be changing, because you actually you have approximated a solution that's no longer actually true. In model-based RL, the dynamics are changing. However, you have this planning step in the end. So actually you can't just use the change dynamics to do your planning in model-based RL. So this is really something very, very, very convenient for model-based RL. And when it comes to exploration, however, we did not really talk about exploration so far. We only saw epsilon greedy for value-based RL methods or entropy methods for policy gradients. However, this is really something really trivial ideas. We will see a lot more exploration strategies when it comes to the exploration strategies lecture. And you will see that there's a lot of components that are actually building from the model-based RL area. And you will see that there is much richer forms of exploration that you can actually use if you do model-based RL. We see a lot of this in the exploration strategies lecture. Okay, so why model-based RL? I hope this is somehow clear. So the question is, if we're talking about model-based RL, what is a model in the end? So what is a model anyway? What are the inputs to a model, and what is a good model? And if we want to start with this, we first should define what a model actually is. So let's just do a quick recap. I think at the time now it should be clear for everyone. A quick recap on sequential decision making. So actually what we want to do is we want to find the policy that is actually maximizing our discounted future rewards, so our return. So this is actually what we want to maximize, subject to that the actions that we take are actually given to a policy that takes the state and gives us the action, and that the subsequent state st plus 1 is subject to some transition probability or some transition function that actually takes us, given some state st and an action at, the state st plus 1, which in the model free setting is something that we sample from the environment. And what we usually do is we collect data from the environment. So we actually collect tuples st, at, rt plus 1, st plus 1, given through the interaction with our environment. And in model free RL, what we actually did is we learned the policy directly from that data. So we got the data, and what we actually had in the end was our policy pi. We either did this through estimating a Q function, so a state action value function, through Q-learning or deep Q networks, or we did it directly using policy gradients. So in the end, we had a policy. And turns out that if we're doing model-based RL, what we actually want to have is, we want to first learn a model. So we actually also have collected experience samples from the environment. And what we usually want to do is, we want to learn a model of the dynamics of the world using that data, and then we want to use it to learn or improve our policy. So actually we want to extract some function f from our data set that describes the dynamics in our environment or in our model, and using that we want to actually in combination or alone from this, we want to actually compute our policy from it. So this is actually what we want to do in model-based RL. And question now is, how could this function f look like actually? And what is actually a model? So what we actually see is that, or what we can actually say is, this is also borrowed from the model-based RL tutorial from ICML. A model is a representation that explicitly encodes knowledge about the structure of the environment and the task. And the question is, what knowledge should we explicitly encode? And it turns out that we can encode a lot of things. So we could actually encode a transition model. This is actually something that is really it comes up to your mind immediately. A transition model just is a model that predicts, given a state and an action, that predicts the successor state that actually is coming next. What we also could actually predict or encode is a reward model. So we actually get a state and an action, and we predict what reward we will gonna receive if we actually take this action in this state. What you will also see a lot, or not so often, but what you also see in practice is something like an inverse dynamics model, which is something like, if you have a state st and a state st plus 1, predict the action that actually took us from st to st plus 1, which is an inverse dynamics model. We will see this a lot. So these ideas we see a lot also in the exploration strategies lecture, where we actually kind of build our exploration ideas building on top of the model, because this is actually a measure on how good we actually understand the environment. We could also see something, we can also train something like a distance model, which is actually given some state as y and as j, that actually gives us some measure of distance, like a metric number that tells us how many steps we would actually need to take coming from one step to another. Or we actually use a future return model, which is something like a Q function or a V function, which is actually something that we also learned in the past. However, if we talk about model-based RL, what we actually want to do is usually we want to train a reward model, and we want to train a transition dynamics model. This is typically what model-based RL is doing. So now, if we actually want to use or want to train through experience samples a transition model or a reward model, question is now, what models can we actually use to do this? And also in here you see actually different dimensions of how you could actually build such models. So the first dimension is you can either use parametric models or non-parametric models. So very what you see in the beginning, what you usually use. in modern machine learning classes, if you use something like neural networks in here, or Bayesian neural networks in here, where you just learn parameters for a model that actually lets you predict, let you be used for training your dynamics model. And what you also can do is you can have a physics-based model, which basically means that you have a certain that you have some differential equations that actually describe your physics, and you want to parameterize your known physics models, like you have your card pole and you know all the dynamics in the card pole, and what you actually want to do is you want to do something like system identification, and you want to actually get data to actually estimate like the pole length, and you want to estimate like how your physical model is being parameterized to actually work for the given environment. There's also a lot of non-parametric models in here, like Gaussian mixture models and also Gaussian processes, and also decision trees or random forests. Especially Gaussian processes is something that we will see at the end of the model-based RL lecture again. That is like the family of non-parametric models. A very easy non-parametric model that is not on the slide in here is something like a replay buffer, like a really big replay buffer that covers the whole distribution of your samples. So this is like a non-parametric model, because actually the experience replay buffer would actually have all the samples in there, and you can actually access and actually extract the physics or actually the dynamics from that replay buffer. There's also like transition graphs to actually identify transitions between data points, and then you can actually interpolate between them. So this is like what you can lose for non-parametric models. However, in the second dimensions actually, which is in practice a very more relevant question in practice, actually how can you represent your features, or what's actually the input to your parametric or non-parametric representation. So actually, do you use states? Do you use observations? Do you work with latent states? And this is actually something that we will cover in the first few slides. This is actually what I already said. So you have a dynamic system. You can do like system identification in here, or you can use neural networks in there. So actually, if you use states as an input, so you actually know all the so like in card pole. So if you know the states, what you can actually use is you can directly plug the state information in this case, differential equations, and you can easily come up with an hypothesis what the next state is. So like modeling a system through differential equations is really something that's really popularly been done in classical control theory, where actually what you actually learn in there is you do the system identification, so you parameterize your model, and then you actually use the differential equations that describe your physical systems using the state information that you get. For instance, in card pole, you immediately get the angle of the velocity, and you can immediately use it to put them into your differential equations. And if you have a look into the implementation of card pole in OpenAI Gym, you exactly will find something like this. However, this also requires a lot of domain knowledge, because you need to model everything. You need to model the physics and how physics is interacting with it. And the question comes up, why actually don't you use something like an MLP for this? Can you use actually a neural network instead of describing your system through differential equations? And actually, what you can do is you can use an MLP actually to learn the dynamics of a dynamic system. So in this thing, what you would do, you would just put in, you would just observe like a real card pole experiment, and you would actually measure all these sensor values, and you would actually using this data, you would actually predict a dynamics model. You would actually train a dynamics model that captures all this information. So this is something that you can easily be doing with a neural network in here. Turns out that in practice, it is much easier to actually not predict the full state. So if you have an input ST and AT, and you want to predict the output ST plus 1, it turns out that it's usually a better idea to just predict the updates of the residual that is actually being added to your original state information. So actually only predicting the changes, because you have a much lower variance target in there. And you also already, of course, can combine this with something like an RNN. So because you have usually a time series, and if you have some long-term relationships, you can also use an LSTM for that. This is something that you can usually do if you have state information given from the environment. However, usually you do not have state information. So if you actually consider high-dimensional state spaces, such as images, there is no state information. You just get an observation. And what you actually can, so actually our input is now not in state space, it is in pixel space, if you talk about images. And if you talk about LiDAR scans, actually you get like a rotational distance. So you get within a degree, you get a distance to certain objects, which means that we do not actually know the underlying state. Might not necessarily mean that we have a POMDP, however, it just doesn't mean that we cannot extract the state information from it. And what you can actually learn from there is you can learn something like an observation transition model to predict the dynamics. Like in this paper in here, what they actually did is they predict the dynamics of a pants during a folding process. And what you actually see is that if a robot is doing something, you can actually see how the folding is being doing, and you see some blurriness as you predict into the future, because you actually directly predict in the pixel space. This is something that, of course, needs a lot of training data to be working very well in practice. This is actually why it is not very common to actually work directly on the pixel space if you talk about image-related RL. What you actually do very much more often is actually you work on something like a latent representation. What you see in here is a very early example where you actually, so the basic idea is that you have, if you work in images, what you actually could use is you could train something like a deep autoencoder with some convolutional layers, and you get something like a latent representation from which you actually could, if you want to, you could actually reconstruct the original image. However, in practice, we do not want to reconstruct the original image. We would just want to use this latent representation as something like a state encoding that we can actually use as an input through for our dynamics model. So we could regard this or consider this latent representation to be something like a lower dimensional feature space, which we can use actually as an input to our policy, as well as the input to our model that's actually learning the dynamics. And as the latent space is usually much lower dimensional, this allows for much more computation in practice. And during training, we actually would not need to reconstruct the observations. So we only need to compress them through the first stage. Another idea is actually very similar to this. However, it here encodes also the idea of POMDPs. So what you see is what you always might be accounted for in DQNs. If you have something like if you want to build a markov state out of your pixel input, what you could actually do is you could stack actually the frames. You can have something like also something like an autoencoder structure. And what you actually want to do is in this one, you want to have 4 input states, and you want to predict from these input states, you want to predict the next state in here. And if you push this something to your bottleneck in here would actually encode everything that is necessary to actually encode the next frame, and you can actually work on this latent representation to actually train your model. So this is actually something that is very well practiced currently, and which is something very popular lately. Also very popular lately is something like that's called word models. So the original idea is, that if you, for instance, if you look a little bit around these pictures, what you see is your head is getting tricked while looking through this on this picture. So this is a little bit wobbling in here, and you also see something like coming out on this image, which is actually something that your brain is a little bit tricked with these examples. And this is actually because your brain or you as a human has some internal representation of what's happening using this input information. This is also the idea that has been exploited by this approach. So the principal idea is to say you have a high-dimensional image representation, which is actually your observation, and you take many observation samples from the environment and train a variational autoencoder from it. So this variational autoencoder also has something like a latent representation, so mean and variances that describe actually your distributions in here from which you could reconstruct images. However, they use this, so actually what you can do is you can actually train this in an unsupervised manner, so you just have an agent that's running through your environment, you train a VAE, you have the images, all the images, and get some latent representations from it. You can actually train an MDN RNN, so a mixture density recurrent neural network, to actually predict what's happening next. And you can actually use this information together to just come up with a linear policy, because it's so easy in this case. You come up with a linear policy that's actually learning how to behave in this setting. So the MDRNN provides to the policy not only the predicted state, but also like the hidden representation of the state. Okay, so how to actually make some desiderata on it, which model to use. So it is, in the end, it's really like something like a trade-off. So actually, we want to have, we want to do a sample-efficient learning process. So we want to interact with the real system as little as possible. So we have limited time and safety constraints. We have hardware wear and tear, and this is something that we actually want to have. We actually also want our model to be accurate over multiple steps. So we require our model to be able to accurately predict several time steps into the future. So actually, remember, one step rewards versus a discounted return, which also has actually this motivation that our model and that we have a stochastic environment and noisy environment, and this is also something that we want to have. We want to have we have a requirement on engineering and domain knowledge. So the question is, how easy is it actually to design a simulator for the real system using basic physics, and how accurate is such a model in the end? And also, does it make sense from an economical perspective? So if you actually know what's happening, you could design a physical system and actually simulate what's happening and actually make some model to actually correct for small mistakes. However, does it make sense? This is always a question. And also the prediction speed. So actually, can we deploy this in a real-time system? Okay, so there's different models. So if you actually see if you have different ways of encoding your models and you have the certain requirements, you can actually assign a little bit the disadvantages and advantages of these areas. And it turns out that for many ideas that you actually follow, there's a trade-off to actually which things to use, and this gives you something like an intuition of how you can actually create your models that you actually been using for model-based RL in the specific setup and problem and task you actually have at hand, and then you can actually look what's best fitting to your environment and how to actually use the model then in practice for model-based RL. So in the next lecture, we will talk about background planning in model-based reinforcement learning.